Hey everybody, Mike Hoffman here with Keysight Technologies with today's installment of the Keysight Oscilloscope Webcast series here on YouTube. Today's topic is really exciting. It's advanced measurements and analysis using oscilloscopes, specifically our InfiniVision X series oscilloscopes. This webcast is really useful for you folks who have found the signal of interest, have been able to trigger on it, and now you really want to do some deep dive analysis and some root cause analysis and find out what's causing that problem. We're going to be going over jitter analysis, how to make different advanced measurements, math functions, and a bunch of other great stuff. Now, I will say that if you're having trouble triggering or taking pictures of the signal you want to measure, this webcast here may be of interest to you. It's all about how to use the advanced trigger methods within our oscilloscopes. Without further ado, let's go ahead and take a look at the agenda. By the way, if you'd like to jump ahead and look at other items in the agenda, there's time tags down below in the description to save you some time.
Today's agenda will consist of a brief overview of the advanced measurements, math functions, and analysis tools available on InfiniVision scopes, and then we'll follow that with a closer look at several debug examples, and then we'll wrap up with a summary before taking any questions. In order to trigger on a problem, you need to be able to see the problem first, and once you're able to see it on screen, you'll be able to analyze it with a variety of measurements. So let's take a look at the measurements available in our scopes today. First, let's start with voltage measurements. There's a variety of measurements here on screen. Let's take a minute to look at each of those. The first 6 measurements are absolute and closely related. InfiniVision oscilloscopes feature built-in help text with diagrams for each measurement, which are summarized here. The most popular 6 measurements are maximum, minimum, top, base, amplitude, and peak-to-peak. The peak-to-peak value is the difference between maximum and minimum values. The top of the waveform is the mode, or most common value, of the upper part of the waveform, and the base is the mode of the lower part of the waveform. If these aren't well defined, maximum and minimum are used respectively. Amplitude is the difference between the top and the base values. In this example, we have a waveform with some ringing, and on the right is the set of measurements that we just looked at. And you can see here that peak-to-peak and amplitude are in fact different. Peak-to-peak is listed in orange, which means the cursors on the waveform are showing that measurement. If you tap on a different measurement, a context menu appears. Below the clear measurement option is track with cursors. Tap this, and the orange cursor lines are now driven by this measurement. This is true for all measurements inside of our InfiniVision X series oscilloscopes, if you want a little bit of extra visual context as far as what's being measured. If you ever forget what measurements are being made or how it's exactly being made, just press and hold your fingertip on the measurement type selection box for 3 seconds. And that's when the built-in help will appear inside the oscilloscope. Some other useful voltage measurements are useful tolerances often required in designs that are exacerbated by excess inductance or ringing in a circuit. Overshoot is distortion that follows a major edge transition, expressed as a percentage of the amplitude, and pre-shoot is distortion that precedes a major edge transition, expressed also as a percentage of amplitude. Using the same ringing signal, overshoot is shown here with the cursors as a reference. And then we'll tap and switch over to show the cursors viewing pre-shoot, again as expressed as a percentage. Finally, there's a wide variety of averaging measurements. There's a simple mathematical average, a DC RMS, AC RMS, and ratio measurements. Each of these 4 having an N cycles and a full screen variant. An average is just a mathematical voltage average of the entire waveform. DC RMS is the root mean square of the waveform on screen. AC RMS is the RMS measurement with any DC component removed, and ratio is a measurement of AC RMS ratio between 2 of the channels in the oscilloscope that you can define. Now there's a difference here between full screen and N cycles, so let's talk about that. You may have seen that before in a measurement list and wondered what that means. In fact, I've worked with some top engineers who also aren't quite familiar with what that means and come to us with questions of why their measurements aren't correct. Full screen will take each measurement across the entirety of the screen, regardless of what's displayed. An N cycle measurement is useful for repetitive signals. As long as at least one period is on screen, or 3 edges, the average will be gated across only one cycle, or N cycles, of the waveform, which means that you don't have to perfectly line up a cycle or a period of the waveform on the edges of the screen to get an accurate measurement. N-cycle and full-screen averages can be wildly different depending on the signal, so let's take a look. To exemplify how full-scale and cycle averages can be different, we'll use the same ringing's pulse here that we've used before. Notice how there's nearly a 100 millivolt difference between the measurements. That's because of the time-based scale being used. There's a higher duty cycle for this signal across the whole screen than for the gated area shown with the cursors, which is exactly bound by 2 cycles of the signal. This is because the whole screen measurement is assuming what is on screen is not repetitive. So if you're using a repetitive signal or measuring a repetitive signal, make sure to use the end cycle measurement and have at least 1 or 2 periods on screen for an accurate measurement. Next are time measurements. Period is the time period of a complete waveform cycle, of course, measured as the time difference between the middle threshold crossing of 2 consecutive like polarity edges. That's a mouthful, but it's essentially 2 consecutive rising edges or 2 falling edges. Frequency is simply the inverse of the measured period. Rise time is a measurement of how long it takes the signal to transition from a low to high threshold, with fall time being the opposite. A positive pulse width is the time delta between consecutive rising and falling edges, with the negative pulse width being the time delta between a consecutive falling and then rising edge. The low, high, and center thresholds default to 10%, 90% for low and high, and 50% for mid, respectively, but they're user adjustable within the measurement settings menu listed with the arrow below. So let's look at how the thresholds affect these measurements, because it's something you want to be aware of. So here we're tracking the rise time measurement of this ringing signal using 10 to 90%, which is pretty standard for lower speed signals. The rise and fall times are both around 45 nanoseconds. But if we switch these thresholds to 20% and 80%, we're seeing a drop in the measurement value, and this is of course to be expected because it's going to take the signal less time to rise from 2080 than 1090. 2080 is more of a common measurement threshold setting for high-speed buses where lower voltages are involved, and many times 10 and 90% levels can be lost in the noise floor of the signal. Some other time measurements include the 2 duty cycle measurements. One is for positive and one is for negative, and an automatic bitrate measurement. Duty cycle is simply measured by what percent of the signal lies above or below the center threshold that you set. And bitrate is measured by looking for the smallest pulse width measurement on screen, positive or negative, and inverting it. This only works correctly if there's a single isolated bit somewhere on screen for the signal you're trying to measure. Otherwise, if there's not a single isolated bit, you would maybe see an inaccurate measurement. So you just got to make sure that's on there, and then it'll automatically calculate bit rate for you in bits per second. Some final automated measurements outside of voltage and time include pulse counting, edge counting, and area under the curve measurements. Area has a cycle and full screen variant similar to the averaging measurements we saw before. This is useful for power measurements or things like that. Next, let's take a look at some math functions that are built into the oscilloscope as well. Now, this is something a lot of people don't really dive into too often, so hopefully this will be some useful content for you and give us some context for the examples that we'll look at later. So, in addition to the automated measurements, we can manipulate waveforms as math functions, and they're divided into 4 sections. Basic operators, which can only be used on analog channels, which are add, subtract, multiply, divide. We also have transforms, which include various advanced functions, filters, and things like that. We also have a section specifically for filters as well, and visualizations, which are purely for deeper insight into the signal. Now, math functions can also be cascaded. For example, you can set up a multiply operator between channels 1 and 2, and then differentiate. This is useful for power measurements that require a voltage and a current channel. And you can also define up to 4 functions and display any number of them depending on your oscilloscope model. The 2000X series has a subset, limited set of these functions. Only one math function can be displayed, where the 6000X, for example, can have all 4 math functions showing at once. So just check the data sheet and make sure you're getting the functionality you need from your scope. Basic operators act just as you would expect. In this example, we're looking at 2 functions at once. Math 1 is subtracting channel 2 from channel 1, and Math 2 is adding them together. There's also dedicated scale and offset knobs for these math functions. When the front panel key is lit, you can see a white arrow next to the math function, so you can move and scale the math functions about on screen, like your waveforms. There are plenty of transforms, and we could spend a whole hour talking about just the transforms, but the most popular is FFT, which gives you a spectral view of the signal on screen. The settings are similar to a spectrum analyzer, in which you either set a center and a span for the frequency range or a start and stop to determine what you want to look at. Center and span is common on spectrum analyzers because of their narrower capture bandwidth, so you generally tune to a center frequency and then span out from there. But since a scope is essentially a wideband digitizer from DC to the scope's bandwidth, start-stop can often make more sense if you want to look at starting at 0 up to a stop frequency. On the sidebar here is a few measurements on the spectrum, namely the maximum power of the highest peak and its frequency, as well as an average power across the span. Now, I mention this because you can combine these two. You can make measurements on the math waveforms. Next is the filter section of math functions. So here's our signal, again with the ringing on it, and using this low-pass filter operator, we can simulate the effects of a 5 megahertz low-pass filter on the signal. We see the overshoot has been reduced by 93%, but the rise time has also increased by about 90%. So if rise time is less important than overshoot on your design, this would tell you a simple 5 megahertz low-pass filter would be suitable to reduce the ringing of your circuit, as opposed to finding the root cause of the ringing or redesigning the circuit. You can also combine a low-pass filter and a high-pass filter to create a band-pass filter. Another useful filter, especially on small signals, is smoothing. So here we've taken a phase-shifted signal and reduced the shift of channels 1 and channel 2 by 1 degree. So subtracting the waveform results in a really, really small low-level signal with a poor signal-to-noise ratio. And you can see that as the big, thick, jittery-looking math function on screen. So if you do this and say, oh, I want to look at the frequency of the signal, and you go to make a measurement on that, you can see the standard deviation of the measurement is basically completely useless. You can see that this is going to be a bunk measurement. So if you add a smoothing function to that subtraction function, you can see that the measurement now is much more accurate. Smoothing is basically a mathematical version of the averaging in acquisition mode. It uses a boxcar averaging of whatever you're putting into it. Another popular filter is the envelope function, and it's actually one of the highest requested math functions we've received for the last few years. This is commonly used for amplitude modulated signals. It's a demodulation function that uses the Hilbert transform to create an envelope. It can be further smoothed like the last example if desired, and in this screenshot we're also leveraging an advanced measurement option that allows us to create custom ranges to measure between, called gated measurements. It's accessible in the measurement settings menu. For this measurement, we're seeing an average 123 millivolt peak-to-peak difference on the top of the envelope between the cursors. Finally is the visualization section. So there's a handful of very versatile visualization functions. First I'll mention is the max and minimum hold. Pictured here is a max hold function cascaded on top of an FFT. And the max and min hold measurements were actually designed specifically for FFT use, because checking for maximum and minimum values on an analog channel is really better served with measurement statistics. For example, if you wanted to check for maximum extreme peaks of peak-to-peak noise or something like that. So max and min hold are very commonly used on spectrum analyzers. And you can see here we're doing a max hold on our FFT, and it gives us a better idea of a worst-case noise floor for the signal that we're measuring. The next visualization we'll talk about is measurement trends. It's a great way to visualize how a measurement value changes over time across a screen. And listed to the right are measurements that can be trended. Many cannot be trended. Amplitude, for example, cannot be trended because it's already a function of time. In this image, we're trending frequency over time by plotting the inverse of each period of this chirp, and we can see a clear linear sweep in frequency over the course of the burst. Using some cursors and automated measurements on top of this, we can conjure this chirp goes from about 0 Hz to 1 megahertz at a rate of roughly 9.8 gigahertz per second. And this is shown via the max and min functions on the top half of the sidebar. And then the automatic slew rate measurement made via the cursors on the bottom of the sidebar. All right, so next let's take a look at the advanced analysis tools built into the box. The 6000X series is the superset product of the InfiniVision line and thus has the largest set of features of all our InfiniVision scopes. And included in those are color gradation, a 10-digit counter, a 3.5-digit digital voltmeter, histograms, mask testing, power supply measurements, real-time diagrams, and a few specific features for triggering on videos or decoding USB or doing USB signal quality testing. We're going to talk about the important ones here. There's a few others that have very niche applications that you can find more information on Keysight.com about if you're so inclined. But let's take a look at some of these advanced tools next. So color grading is now possible for the first time on a non-Windows oscilloscope from Keysight, and color gradation gives you a better 3D view than a standard waveform intensity gradation. It can also be applied to analog channels or math functions. Here we're seeing it on an AM signal, showing a clear distinction between the high and the low levels, making obvious also a large gap or glitch in the center of the signal. Here we can see it on an FM signal, but we're applying the color gradation to the math function, which in this case is an FFT, which gives you quick insight on where the spectrum's power spends most of its time. The 6000X series also comes standard with a 10-digit counter, which provides unprecedented measurement accuracy for frequency and period measurements on an oscilloscope. In this example, even after over 13,000 measurements, the statistical mean, which was shown to be exactly 20 megahertz, is displayed down there, but we can see upon enabling the counter that there's a slight deviation from this intended frequency of only 162 hertz, which would be near impossible to measure without this dedicated hardware built into the scope. A neat thing, too, is it also operates independent of the acquisition system, the benefits of which will be explained in more detail shortly. And finally, the counter can be used on the trigger circuitry, telling you the frequency of a trigger-qualified event. We'll take a look at that actually specifically in one of the debug examples later. Bundled with the counter is a 3.5-digit DVM, which features auto-ranging capabilities, and because it can be operated completely independent of the acquisition system, there's some really neat things you can do here. So in this example, channel 1, you might notice, is completely turned off. You can see it because the channel 1 indicator on the top left is not highlighted, but the DVM is still operating and making real-time measurements on that channel. So how can that be? Well, that's because the DVM is a completely separate piece of circuitry from the acquisition and memory system. So it can be running even when the channel's off. Now, what's the benefit of this? Well, let's say you're not needing to use channel 4. You can plug a standard 10-to-1 passive probe into channel 4 and set the DVM on channel 4 and use it to browse around and make quick and dirty DVM-style voltage and frequency measurements without dedicating an entire channel to it on the scope or having to scale it or turn the channel on to make measurements. So pretty useful and nifty in a pinch. The histogram analysis feature provides a statistical view of a waveform or a measurement result. As waveforms are acquired and displayed, or as measurements are made, a counter database accumulates the total number of hits or measurements, and the histogram data is displayed as a bar graph on the graticule. Statistics are also displayed in the sidebar dialog over on the right. And now in this example, we're plotting a histogram of period measurements on a clock with jitter. And after a few thousand of these measurements compiled, we can see a bimodal distribution plotted on the histogram. Now, some of you who are familiar with jitter or high-speed applications might know exactly what that means, and that's the kind of insight this is designed to provide. For those of you who are going, what the heck are you talking about? We'll dive into that a little bit further in our examples later as we diagnose some trigger jitter, things like that. Our next advanced analysis feature is mask testing, or commonly called pass-fail testing. And Keysight offers hardware-based mask testing integrated into our MegaZoom 4 ASIC that allows us to test up to 250,000 masks per second, which allows you to do Six Sigma testing in a matter of seconds instead of hours. Pretty powerful. Now, you can create custom-defined mask files in a text editor on your computer, or you can download pre-made masks from Keysight.com for many popular serial bus standards like USB or the military standards. Or you can simply use the AutoMask feature, which is a one-press feature that creates a mask automatically for repetitive signals. The mask we're looking at here was created on a PC using a standard text editor in order to create an eye diagram of our data line on a serial bus. Now, if we want to look at the auto mask feature, it's shown here on a clock signal. We got some random crosstalk artifacts popping in and out in the signal. We'll look at this signal more later in our debug examples, but you can see here that in a matter of seconds, we've already done hundreds of thousands of tests, which can be up to 1,000 times faster than software-based mask testing solutions that you can find in other platforms. The next analysis feature in the list is Keysight's powerful switch mode power supply measurement suite. Now, whether you're designing a switch mode power supply from scratch or integrating one into your device or verifying off-the-shelf performance of a third-party unit, these measurements are fully automated with highly insightful with a lot of insight into the performance of the switch mode power supply that you're designing or testing, what have you. Now, we divide these measurements into 3 categories, and this tool allows you to see really a complete picture of the AC input line analysis, performance of the switching device, and the output characteristics on the DC side. And as an added bonus, there's some brand new measurements that you can see on the bottom of the list there that allow you to view the rejection ratio of the power supply or view the frequency response of a circuit, or as commonly called the Bode plot, which is great for any design where frequency response is critical. So if you're interested in that, we have some white papers on our control loop response and actually this entire suite of power supply measurements on Keysight.com. So as a quick example of what this tool provides you, we're looking at a power quality measurement. 9 measurements are automatically created and statistically compiled with the simple press of one button that you can see down below. Now, if you press the Signals menu from within the Power Supply Measurement Suite application, you're going to see a complete diagram of probe points and an auto setup key, which sets your triggers, your scaling factors, and inputs all the measurements under the sidebar. And we also put a D-skew button down there because skew between voltage and current probes is a really big concern when you're making power measurements, because really the point of interest is the switching point. And if there's any skew between the probes, your power measurements are going to be all off. These features that you're seeing here, the pictures of the probe points and the auto setup feature, it's inherent to every measurement in this suite. And it's available on all of our InfiniVision X-Series scopes except for the 2000 X-Series. The next one here that's exclusive to the 6000X is an eye pattern generator, and it's a powerful way to evaluate the signal integrity of your design. The jitter and real-time eye option provides a color-graded eye pattern analysis based on a recovered clock, which we'll again look at here in our examples. It's especially useful for embedded clock designs where there's no explicit clock line. So to create your eye diagram, there has to be some mathematical calculations involved. And in this case, data bits are folded on top of each other for every clock cycle, giving you a 3D view so you can find signal integrity problems quickly and easily. The clock recovery methods I mentioned earlier, they're essential elements to any jitter measurements on an embedded clock design. And we offer a constant frequency method, a first and second order PLL recovery, or explicit clock options for when you do have a dedicated clock line that you can probe with one of the other oscilloscope channels. You can also combine this with the histogram feature for some really quick insight. So here we're looking at a distribution of edge crossings on our eye diagram. And here we're seeing a Gaussian distribution that's telling us that there's no deterministic jitter on the signal. So we'll dive more into that a little bit here in a second in our next section coming up, which is our debug examples. So let's jump into those. So these are going to be some real issues that we've seen out in the field. So we're going to dive through how this gigantic list of great features can combine together to solve and find root cause of problems for you. So in this first example, we're seeing an intermittent read-write error on a high-speed data line, and we're trying to figure out what's causing it. Now, we know that this bus has a dedicated clock signal, so the first step we're taking is to simply probe the clock line and look for anything unusual. Now, the InfiniVision X-Series scopes have a really fast update rate, so we're seeing an intermittent glitch popping in and out in the clock line pretty readily, and we're believing that it's some sort of signal coupling issue, and narrow it down to 3 potential causes. There's a nearby 1 megahertz clock, a 24 hertz switching signal from a power supply, or interference from a nearby radio operating at 190 kilohertz. And your job as the engineer, put your engineering hat on, is to figure out what is causing that and how you can solve it. So first thing we do is set up a advanced trigger to isolate on this glitch. So we have a time-based setting of 20 nanoseconds per division. It was pretty easy to eyeball the glitch as roughly 2 or 3 divisions wide, so 40 or 50 nanoseconds, while the regular clock pulse is much wider. So we first set up a pulse width trigger that isolates specifically on the glitch. In the trigger menu, we change the type from edge to pulse width, and then we define the settings to look for a positive pulse less than 15 nanoseconds wide on channel 1, which you see circled down below. And then as you see on screen, we've locked in on the glitch. So now that we've locked in on it, ignoring all the other good clock pulses, we can dive deeper on the problem specifically. So let's try using the counter and see if the frequency of this problem or glitch is constant. So we start, follow the red circles. If you're curious on the button presses, hit the blue sidebar key to pop that open. And then we'll select the counter feature. And then once we have the counter turned on, it's showing us a frequency of 3.57 megahertz. Now that's the frequency of the clock signal itself, not necessarily the frequency of the problem we're seeing on screen. So what we do is tap our gray frequency button to modify the settings. And then we change our source from channel 1 to trigger qualified event, which is at the bottom of the list. And then we tap the X to close out, and we can see that, we have a very constant frequency of the trigger circuitry at essentially 24 hertz, which is telling you this glitch is likely connected to that switching source on your design. Pulses like this, as you have probably seen before, are often caused by powerful, fast edges cross-talking into the signal, so it's not too big of a surprise. Let's take a second example here. We're going to be looking at an automobile. The CAN bus, which is being used in this example, is a popular, easy-to-use, and robust bus that is heavily used in automotive, marine, manufacturing, medical, and heavy equipment markets. And Keysight's unique translation capabilities allow us to see frames with text descriptions instead of just simply hex or binary decodes. So you can go ahead and visit keysight.com for more information on this feature if you want to dive into that. So we had a few automotive folks in the audience. So in this scenario, we're seeing a number of errors on the bus originating from the steering wheel assembly. Now, are these litany of problems purely coincidental, or is there a correlation between all these errors that are appearing on the serial bus? And if we can find a correlation between the errors, we can probably find the root cause. First, let's change our trigger settings to the CAN bus and trigger on all errors. We're now viewing exclusively errors on the bus. In this case, we're zoomed in seeing an airbag error, but we're also seeing errors from a couple other pieces of hardware, such as the airbag, an ABS system, things like that. So what we want to do is try to find some sort of correlation or pattern between these errors. So let's try the counter like we did before. So using the counter as we did in the previous example, unfortunately it's not producing a useful result. The frequency is actually bouncing around at different values, telling us these errors aren't perfectly patterned. They're happening at non-regular intervals. So the frequency we're seeing here, such as in this example, not constant. So we need to try something else. So we're going to pull another tool out of our toolbox and use something called segmented memory, which allows us to acquire consecutive occurrences of a trigger and compare them to one another. We're going to tap the Acquire front panel menu, and brings you to this menu here on the scope, and where we're going to press the segmented key. And in this menu, we can simply define how many consecutive triggers to digitize. So we'll tap number of segments, and we'll key in, for this example, 50. So I'll type 50 on the on-screen keyboard with my fingertip, and then tap the segmented button to begin acquisition. Segmented memory can be used on events of any frequency, and in this case, the bus is producing errors at a rate of more than 1 per second, but this tool can be used on events that occur once an hour, once a day, or longer. The scope will sit and wait for a trigger event, digitize it into one of 1,000 available memory slots, and then go back to sleep and wait for the next event. So the maximum number of segments we can acquire is 1,000. Okay, all done. Now that 50 segments have been collected, we can review what the scope has captured. Each segment is time tagged in reference to the first segment with the timing resolution accurate down to a sample period, so very accurate. And you can see this over on the left-hand column or on the right in the event lister. If you tap the double down chevron arrows, which you see circled up near the top, this table can be made full screen for easier viewing if you're not so interested in looking at the signal. And in this view, we can see more information. But if we look at those time tags over on the left, it's giving us again in reference to the first segment, where it actually would be more interesting for us to see it in reference to the previous event. And we can change this in the lister menu. So we tap the gear icon up at the top, and then tap lister menu. And on the bottom soft keys, we're going to switch it from time reference to the trigger to the previous row. And now we're seeing a pattern emerge in the errors. Each error is occurring at a set time after the previous one in a repeating fashion. And this tells us with certainty that these errors are in fact correlated, given the repeating nature. And they're probably coming from a failure in the ECU, or engine control unit, which is essentially the master in this bus configuration. Because we're seeing errors not only from the steering wheel, but we're also seeing it from the ABS and a few other places. So what this allows us to do is dedicate R&D resources to an ECU redesign instead of troubleshooting parts that are not faulty, like the steering column. For those of us like myself who are picture-oriented, here's kind of a picture of how segmented memory works and why it can be useful. So memory depth on the scope is fixed. So as you want to capture more time, such as consecutive events, the time between each sample is longer, and thus your sample rate goes down. If the sample rate goes down far enough, the signal you're trying to capture may be undersampled or aliased. And additionally, if the problems you're searching for are rare enough, this method may not work whatsoever, such as in this picture example I created, where the event of interest, or these pulses, are so far away that we've zoomed out our screen with the trigger in the center, but we're not even capturing anything in our single shot. So doing a single shot and searching for it would actually be a lost cause in this case. So our solution to that is segmented memory, which, like I said before, will take a snapshot of the trigger event and a user-defined period of time before and after that event, and then all the dead time in between that you're not interested in is not digitized. You can do up to 1,000 of these segments, and essentially you can expand your memory depth indefinitely depending on how infrequent your events are or how many segments you set up. It's kind of like a television that can skip commercials for you. For our third example, we're going to be looking at a slow clock with a high-speed noise writing on top. And if we zoom in our time base to an edge, like we see here on this screenshot, we're seeing a sinusoidal high-speed noise writing on the signal. And our job is to determine the source of this noise. And if it's not possible to shield or prevent it, we're going to need to design a filter to remove the noise from our trace. By turning on the FFT math function, we see a clear spike appearing in a very, very high frequency range of the spectrum, and we can use the automated frequency peak search to identify the noise as around 20 megahertz, with our clock signal being 1 kilohertz, much faster. So now that we know the source of the noise, we can design a filter to remove the noise, but we can also use the oscilloscope to test what filter cutoff frequency we'd like to use. So what we're looking at here in this screenshot is actually 4 functions at once. So we're going to test out a filter design. We'll use the low-pass filter math function on channel 1. Let's try 2 megahertz, and the result is a signal with no more issues with noise, as it's all completely removed, but it does have a significantly larger rise time, as we looked at before. So by leveraging the cascading math function capabilities of the 6000X, we can also see the spectral content of the filtered signal and completely verify that all remnants of this noise spike are now gone. So what you could do here now is in your math function tweak the cutoff bandwidth of your low-pass filter and determine how much rise time am I willing to give up versus how much noise am I willing to deal with. And now you can actually tune this live on the scope without having to build the circuitry and implement it and test it. In this next example, we're going to look at how you can use the jitter application to help identify issues with the system clock. Now, in the picture you see here, you're suspecting that your clock system is suffering from interference from some other signal, but from a visual inspection, you're unsure of the source. First, we'll zoom out the time base to gather a larger set of data for the jitter application to crunch through. And as we zoom out the time base, again, gives more data for the jitter application to use. And now the jitter application does leverage a number of the math functions we looked at before, FFT, measurement trends, and histograms. So let's look at how all these advanced measurements are automated to give you insight on what the source of this jitter is. So let's press the jitter front panel key and bring up the configuration window. You can see there are 3 auto setup buttons with setup keys next to them, as well as 3 configuration keys on the left. We'll start by adding a measurement, which is circled in red. Tapping this brings up a number of jitter-specific measurements, with the time interval error measurement at the top being the most useful here. So we'll select clock TIE and look for some sort of time interval error pattern. Once we select that, the jitter application needs more detail on the clock itself. So the measurement source is channel 1, with the slope and unit preferences changeable at the bottom. Most importantly is the clock recovery settings, so let's go ahead and tap that. Now, once you select that, you'll note there are options for clock recovery method and data rate. So for the purposes of analyzing jitter without any further insight or clock recovery simulation on the receiver, we'll use a constant frequency of 10 megabits per second, which is the clock rate for this signal here. So we'll tap semi-automatic, and then we can go ahead and type in a custom nominal data rate here. Press OK a few times, we'll get back to our root configuration window, and now we can start using the auto setup tools to start getting some measurements on screen. So we'll start with the auto setup measurement histogram, and this creates a horizontal histogram distribution of time interval error measurements across the bottom of the screen. We're seeing a bimodal distribution, which is a sign that our jitter spectrum is deterministic because the distribution is not random. We can then select the Auto Setup Measurement Trend button to see time interval error measured over time across the screen using the measurement trend function. Let's go ahead and close our window out, and we can see that. And oh, look at that. We can confirm the sinusoidal jitter is entering the clock signal. Now this is a trend measurement of clock TIE, and it's also smoothed for us so we can see a nice clean sine wave. Now finally, if you want to understand what the frequency of this time interval error across the screen is, we can add a simple frequency measurement tying it to math function 2, and we can see that there is a 100 kilohertz frequency of time interval error, which can be tied back to a 100 kilohertz switching power supply within their design. So using this tool, we've determined that the power supply is the source of our jitter. So now that we know that we have jitter, and we know that it's deterministic, meaning that we can determine its frequency and its source, we can design some circuitry to remove that jitter on the receiver. It's often done with a loop bandwidth filter. So let's use some of the clock recovery tools built into our jitter application to design a filter to remove this jitter. So let's go ahead and open up our real-time eye diagram tool here, and we'll go ahead and start playing with some of these options. So we turn on the real-time eye diagram, and the first thing we see is a very, very dirty eye. And that's because we have a lot of jitter closing the eye from the left and right from a timing perspective, and due to the slew rate of the clock, it's also closing it on the top and the bottom, similar to noise would. But from what we saw in our signal, we don't have really a vertical noise problem, more of a timing noise problem that we're trying to solve. Now, the color grading here also gives us some insight. We can pretty confidently say there's not a lot of vertical noise based on those white-hot areas taking most of those hits on the top and bottom of the signal. So we can also, again, add a histogram to this. We're doing that here, and you can see that there's still that bimodal distribution on the edge crossings itself. So now let's start doing some of the clock recovery tools here built into the scope to start reducing the jitter using a loop bandwidth filter. So first thing we do is open the clock recovery window and switch from a constant frequency to a first order PLL. Now our nominal data rate is still 10 megabits per second. The ideal loop bandwidth is a combination of an art and a science. With too little of a loop bandwidth, you're not going to reduce jitter enough, and too high of a loop bandwidth will cause an unstable PLL that may introduce even more jitter. So let's start with a loop bandwidth of roughly 1.5 megahertz, which it might be pretty close to ideal because we do have a 100 kilohertz source of jitter, the 10 megabit per second signal. That's somewhere in the middle. Let's give that a try. And our histogram now shows what appears to be a Gaussian jitter distribution, meaning we've successfully removed any deterministic jitter from the circuit, or most of it at least. Any remaining jitter can be attributed to random noise, which is often just resulting of thermal noise, which is known to be Gaussian. So the closer we get to that, the better, because everything outside of that is outside of your control. And we can now verify our design here using the same auto setup measurements we used before. So now we're doing a measurement trend, and we can see that it's an order of magnitude smaller than what we saw before. While the TIE distribution is not perfectly Gaussian, it's no longer obviously bimodal. So you could probably do some further filtering, but with how clean the new eye diagram is, we could probably say our job is complete. Whew. All right, so that was a lot of stuff. So let's take a quick second here to wrap up and talk about what we learned today, and then we'll take a look at some configuration options and some promotions we have going on right now, and then we'll open it up to Q&A. So, kind of in summary here, we looked at over 37 automatic measurements that are again broken into 4 pieces: voltage measurements, time measurements, counting measurements, and mixed measurements that can be ran on analog channels or on math functions. We also looked at some of the over 25 advanced math functions that come standard in many of these scopes that, again, can be cascaded or combined together for not unlimited, but relatively unlimited combinations of math functions that you can put together. And then we looked at some of our built-in analysis tools, such as the integrated voltmeter, counter, and totalizer, color grading and histogram, the real-time eye and jitter measurements, the power measurements, mask testing, and others. As far as what's available on what product, we do have 4 main products on our Infinivision line, from the 2000X up to the 6000X. You have a kind of a wide variety of options here based on your performance needs from a bandwidth perspective, or from a memory depth perspective, or from an analysis options perspective. Of course, as you move up the line, more options become available to you. So go ahead and reference this, or take a look at the website listed above, keysight.com/find/Infinivision, for a detailed breakdown of each of these options, prices.
For our first question, Tim wants to know, how do you access the help diagrams?
We have built-in help all throughout the oscilloscope, so to access the help menus for the measurements or math functions, simply press and hold your finger on that measurement or math function. You can also press and hold any of the hard keys on the entire front panel, and the built-in help will pop up on screen. So any function, any button, anywhere on the scope has built-in help. Press and hold for 3 seconds to access it.
Okay. How can I control how much time is captured in each segment when using segmented memory? I only saw an option to set the quantity of segments.
Good question. So, yeah, you do set the quantity of segments, but to set how much time you want on screen before and after the trigger point, set your scales up as if you were just looking at the signal on a repeating basis. So if you have your trigger in the middle of the screen and you set your time base to look at, say, 10 nanoseconds per division, it's going to automatically capture 50 nanoseconds before and after the trigger event for you. So it's completely set up by you before you press the segmented key.
Okay. Next question is, what is the advantage of the FFT support over a separate spectrum analyzer?
Interesting question. So it's obviously the huge advantage of an FFT is that it's just built in to the scope and the channel that you're measuring. So if you were saying wanting to look at the analog signal and the spectrum at the same time using a standalone spectrum analyzer or a separate channel, you would need to split that signal somehow. And you might be using, say, a high Z input on your probe point for the scope, but then maybe you need a 50 ohm input for your spectrum analyzer. So it makes probing a lot easier to use the built-in FFT. And the built-in measurements of the oscilloscope as well are another advantage. And then the one disadvantage would essentially be the noise floor of the FFT. You're going to have a better noise floor performance on a spectrum analyzer than you would on a scope, but that's just the nature of the digitization. So those are trade-offs to consider. It depends on your application, your bandwidth requirements, and things like that.
All right. How are the threshold settings determined as a percentage of the signal? Can they be set explicitly?
Good question. So the scope is in the background always taking top and bottom measurements, essentially, and that's how it determines the percentage values for the thresholds, but you can also set them explicitly. So if you know you want your center crossing to be, say, 500 millivolts, and you don't want to deal with a percentage, then you can also explicitly define your thresholds in those measurement settings menu.
Okay. The white papers that we're talking about, Bodie plots, could you tell everybody where they might be found?
Yeah, so your best bet is to search on our website for the power supply measurement application, and there's going to be a data sheet and some white papers there. I can also make sure I see that was from Tim. We can make sure to get that to you directly after the presentation.
Okay. Yeah, I also wanted to find out what kind of applications are required for using Bodie plots.
Good question. So the only one, there's two options you need. You'll get them both with the application bundle, but if you have an existing scope, you'll need the power supply measurement application, and you'll need the WaveGen option turned on because it uses the waveform generator to sweep the input frequency.
Okay, here's sort of a general question. How long does it take to become proficient with the 6000X?
Oh, that's a great question. So it depends on how familiar you are with our interface, of course, but I will say that one of our big design goals for all of these InfiniVision scopes is ease of use. We understand that the majority of people who use oscilloscopes aren't using scopes on a multi-daily basis. A lot of people are picking this up off the shelf once a week, once a month, so we try to make it as easy as possible with all the automated setup routines for all the measurements, the built-in help text, things like that. So I would say a matter of just spending time on the scope, probably a couple hours before you can get very proficient with the interface.
All right. With the FFT support, how does it compare with regular spectrum analyzers for measuring white noise?
For measuring white noise, so it depends on the level of white noise because there's two things if you're making measurements on any piece of test equipment. You always have to remember that all test equipment, no matter what it is, has noise inherent to it. So it depends on the level of white noise you're trying to measure. If you're trying to measure a very, very low level of white noise that might be below the noise floor of your test equipment, you have to be conscious of that. But if you are wanting to measure white noise, say, across a wide frequency range, a scope may actually be better than a spectrum analyzer because a spectrum analyzer may be limited to dozens or maybe 100 megahertz of capture bandwidth, where a scope can have, in the 6000X series, 6 gigahertz displayed across the screen. So it really depends on what you're trying to do. That might be a good question to call up our technical contact center here in Englewood, Colorado, and they can walk you through that.
Okay, here's another one that you have to sort of figure out the balance. When would you use a counter to measure frequency versus using the frequency measurement support?
Good question. So if you're using the measurement function, the signal needs to be on screen, scaled properly, stable and triggered, things like that. Where the counter, it doesn't necessarily need to be. It's like a standalone counter on your benchtop where there's not like a trigger setting on your counter. It just works. So that's one reason where if you're just doing something on the side, maybe on a signal that isn't on screen or isn't scaled properly or stable in reference to what you're triggering on, that's where the counter would be more useful. So they're very complementary in that sense, where the measurements are for what's on screen right there in front of you. The counter can be used for a much wider variety of options. And the counter also can measure up to 3.1 gigahertz on the counter, where the measurement function is limited to the bandwidth of the scope that you have.
Okay. Looks like we have time for one more question here. Just in case, if we can't get to your question today, we'll be answering them via email. So, when making voltage measurements on noise, do I use peak-to-peak or RMS?
Good question. It depends on what you're trying to measure. The true measure of peak-to-peak noise is always RMS because noise is random by definition. So you could always have a randomly really high peak that isn't a very honest representation of the actual noise. So RMS is the more accurate way to do it. Peak-to-peak is the quick and dirty way to do it if you're just looking for extremes. But RMS is the true way to measure noise on a signal.
Great. Well, that concludes today's presentation.